So this is going to be a typical Hess's law question. And when you see a question like this, basically when you see calculate the enthalpy change for a reaction, you want to look for two things. A, is it asking me to sum all of the formation energies of the reactants and the products, and you look around and there's no, if you don't see this, if you don't see H delta F, then that's not going to be that kind of question. If you just see delta H reactions like we have here, then that means it's going to be a Hess's law question. And we're going to have to look for a reactants and our products in these three reactions right here. So the first part is looking for our reactants. And our first one is nitric oxide. So where, NO, where are we going to find that?
Reactant?
Yeah, we're looking for NO as a reactant. Nitrogen monoxide. I might as well label them so it becomes a little easier. I tried to label, I must have forgotten to label this one. I labeled the rest of them. So we've got A, B, and C.
A.
So it's a reactant. So NO is a reactant in A. And it looks like it has the right amount. So for now, we'll just write it the way it is. And since these are all gases, I'm not going to bother with the states of matter. But as I said before, it's going to be important that we keep track of those, because changing the state, as we've seen, takes energy or releases energy, depending on what states you're going between. So you have to pay attention to those. But this is completely gas reaction. And let's keep track of our delta H's. So that's minus 198.9. Okay, now I need to find oxygen, but that's oxygen atoms. So that would actually be an oxygen radical. Where am I going to find oxygen radicals?
And the C?
Mm-hmm. Which side?
Product.
Product side. So we're going to have to flip that. Not only are we going to have to flip that, it appears we're going to have to divide it by 2, because we only want 1 oxygen radical. We don't want 2. So let's reverse it and multiply it by half. So that would be O gives 1/2 O2. And what's going to be my delta H for that reaction?
495.
Nope. That's the delta H for this reaction, not this reaction.
142. Negative 247.5.
There you go. Yeah, it has to be negative because we flipped it. Before, it's an endothermic reaction. And if you look at it, that makes sense, right? Because what we're doing is we're taking O2, breaking both bonds. So it's actually going to take a lot of energy to do that. And what we're coming up with is 2 moles of this. 2, 3, 4, 5, 6. So that takes energy to do that. And so when it reforms, when it actually makes bonds, that's going to release energy. That's going to be exothermic. And so we reverse the sign, and it's half. We only want half as much. And so that would be minus 247.5. Right. So I've got my nitrogen monoxide, I've got my oxygen atoms, and now I need nitrogen dioxide gas. Where am I going to find nitrogen dioxide gas?
Reaction A.
Reaction A. And so we already have it there. So let's have a look. Because right now I have all the products and I have all the reactants, but I don't think it's going to add up. Because I have, look what I have in my first reaction. So I'm going to have reaction 1, reaction 2. I've got some things that I can't cancel, right? I've got ozone. Where am I going? Where do I have ozone?
O3.
O3. I've got ozone in reaction 1, right? And that's the only place I have it.
Also B.
Well, B we're not dealing with now because, yeah, that's okay. Yes, that's where we're going to get it. But I'm saying, yeah, in the reactions that we are putting together to balance each other out, I have ozone in reaction 1, but I have I don't have it as a product. I need it now as a product in order to balance it out. So I have 1 mole of ozone as a reactant. I'm going to need 1 mole of ozone as a product so I can subtract that. So, and yeah, I think that's really what we need to do. So I need 1 mole of ozone as a product. Where am I going to get that from? I think you already mentioned, Ilham, you already mentioned that it's in reaction B, 2B. It's in reaction B. So what are we going to have to do to reaction B in order to give us 1 mole of ozone as a product?
Flip it.
Yep, we're going to have to flip it. And what else are we going to have to do?
Change the charge of the heat, delta.
Well, yes, when we flip it, we automatically will change the sign of the heat.
Divided by 2.
Yes, we also need to multiply it by 1/2 because there's 2 moles of ozone in reaction B, and we only want 1. So what we'll do is we'll have 3/2 moles of oxygen, making 1 mole of ozone. So what is going to be our delta H for that? So we've taken B, we've reversed it. So we flipped the sign from negative, and we've also multiplied it by 1/2. So what's going to be our
142.3 positive.
Positive? Okay, yes, positive. And remember to put the sign in. A lot of people make this mistake. I make this mistake all the time. I leave the sign out, even though you see it without a positive and you think, well, I'm going to, I know that means positive. But it's really easy to make that mistake, especially if you have like 4 or 5 reactions and they're all negative or something, and you just look at it real quick and you go, oh, well, yeah, 5 negative, and just add them all together. If you have the positive sign in there, that sort of makes your brain say stop and pay attention to this. So yeah, 142.5. Now, before we add these together, we need to double check and make sure that we're only left with the final reaction. And remember, the target reaction we're looking for is this one up here. We want to end up with nitrogen monoxide plus a single atom of oxygen gives us nitrogen dioxide, okay? So we have our NO.
It's a 142.
Sorry? Well, oh, 0.3. You're right. You're absolutely right. I knew I could count on you to give me my significant digit. 1.3. There we go. 0.3. Excellent. All right. So let's cancel out what we can. So we just put in ozone for the simple reason to cancel it. So we know we can cancel that, right? We have ozone on both sides. We have 1 mole of ozone on both sides, and it doesn't appear to be anywhere else. So I'll cancel out ozone. What else can I cancel out?
Cancel out 1 of O2 and just leave a half of O2. Or you can actually cancel out O2.
I can do what with it?
Cancel out O2.
Right, because look, I have 1 mole here, and I have another half mole there. So I have 1.5 moles of oxygen as a product. And look at this, I have 1.5 moles of oxygen as a reactant. So I get to cross all of the oxygen out. And then if we look, the only 3 things that we actually have left are nitrogen monoxide plus oxygen gives us NO2. And that is our target reaction. And so we can just take these 3 enthalpies and add them together. So what do we come out with?
NO react with O, and then we will have NO2.
Mm-hmm. And what's our heat? What's our enthalpy of that reaction?
Would it be negative 303.9?
303.9 kilojoules per mole.
I got negative 304.1.
Oh, right, because I had that, yeah, because I had that as a 5 earlier. Yeah, so it's going to be negative around 304. So when you get something like that, go back and look at the original reaction and see if it makes sense. And you see from the reaction, we're taking something, nitrogen was only bonded to 1 oxygen, and now it's going to be bonded to another one. So we've actually increased the number of bonds. And basically, if we have more bonds made on the product side than we have on the reactant side, more than likely it's going to be an exothermic reaction. That's not always true because, as we'll find out, not all bonds are created equal. Some bonds are stronger than others, and so the stronger the bond that we make, the more energy that's released. And basically, anything bonded to oxygen generally is a strong bond. So when we form bonds with oxygen, they're almost always exothermic reactions. So that makes sense that we would see that. So everyone see how you have to look and make sure, because after we found all our reactants and we found all of our products, but we still weren't done, because when we looked at what we had in reaction 1 and 2, we noticed that it didn't balance out. And so a lot of times you're going to see things like C, that reaction C. And the only reason that's there is so we can balance our ozone or whatever it is we need to balance on one side and the other. So a lot of times you'll see, just N2 becomes two moles of nitrogen atoms, or in this instance, 1 mole of oxygen molecules becomes 2 moles of oxygen atoms, or liquid will turn to gas, or gas will turn back to liquid. And the only reason we do that is so we can basically cancel everything out that we need to. So is everyone clear on this one, how we did it? Or is everyone ready for their nap? Yeah, go ahead.
Quick question for O2, how you cancel it O2? There is one in the top, 1 O2, and the second has O2, then 3/2
Yeah,
Like,
there's 1.5 moles of oxygen as reactant. That's our 3/2. So that's 1.5. Then on the product side, there's 1 mole of oxygen in reaction 1, and there's another
okay.
and there's another 1/2 mole in reaction 2.
Okay, got you.
Yeah, so we just add them together. So then we have the same on both sides.
Okay.
Yeah, you see why these are, I don't know, I find these kind of fun because if they're like little puzzles. And if you get to the end and you basically you can cancel everything, then you pretty much know you've got the answer right. So it's one of those things like when I'm grading them too. If you get if you cancel everything out and you have everything right, but then you make a dumb mistake with the math, well, I mean, you got most of it. I see you know what you're doing. You'll still get most of the points if you do that. Okay. All right. Next, a question. Or maybe I'll just like pull one out and make one of you do it. How about that? We haven't done that before. Maybe we should do that. Make you share the screen and then you do it for us. That would be mean, wouldn't it? I should start being mean. All right. Oh, yeah, this is a good one. Why don't we do number 2 because there's another step involved. So we need to figure out the heat of formation of liquid methanol. And you remember what the heat of formation is. Anyone give me a definition for the heat of formation? There's a very specific meaning. So if I say I want the heat of formation of CO2, what is that? What reaction is that? So it's heat. It's a heat. So it's a reaction. It means it's the amount of energy involved in a reaction. It's forming CO2, but from what? What? Heat of formation is a very specific meaning. What does it mean? Can I form it from like anything I want? It's basically, I could form CO2 from basically anything, right? I just set fire to pretty much anything. I'm going to form CO2. Is that what I'm talking about? When there's that subscript F for heat of formation, or does it mean something different? And the answer is actually right on the page. Notice there's a heat of formation of CO2 right on the page. What reaction is it associated with?
Combustion.
I'm sorry?
Combustion.
No, not specifically. This one is combustion, yes, because we're combining it with oxygen. But for heat of formation of basically anything, what's different about the reaction with heat of formation? There's something that means something specific. What does it mean? What are you forming it from?
CH3OH.
From moles.
Well, everything forms from moles. But when you're dealing with a heat of formation, a formation reaction, It means you're forming it from something specific. What specific things are you, or things are you forming CO2 from?
Carbon solid plus oxygen gas.
Mm-hmm. And what's unique? Well, also look at water. So the heat of formation of water is right underneath that. And the heat of formation of methanol is right under that. What's unique about all three of these? Look at the reactants.
Solids to gas.
Nope, water's gas and gas. Talked about it in the lecture last night. There's a very
They all
specific.
have O2.
Well, yeah, I mean, there's oxygen in all three. I'll put it this way. Are we forming each one of these from complex molecules? Do you see any complex molecules?
No.
What do you see?
Carbon, hydrogen, and oxygen.
Just, right? You're just forming them from elements. That's the whole meaning of heat of formation. So if I take methane and burn it with oxygen and make CO2 and water, that isn't a formation of CO2. That is not a reaction. It's a reaction that forms CO2, but it is not the heat. It's not the reaction that we can use to measure the heat of formation of CO2. Because when we talk about the heat of formation, it means whatever the constituent elements are only. And it also means the most stable form of those elements at standard temperature and pressure. So carbon, the most stable form of carbon at standard temperature and pressure is graphite. So that would be solid carbon. The most stable form of oxygen at room temperature is O2. It's a molecule, but it is the most stable form of oxygen at room temperature in 1 atmosphere. Same thing with hydrogen. It's a gas, H2. So all that means is that if we want the heat of formation of anything, what it means is that we need to put down each constituent atom in its most stable state, those things reacting together and making 1 mole of whatever it is we're talking about. And in this instance, what we want, basically we want to come up with a reaction that gives us this. That's the reaction we're looking for. We want to end with that. That's the reaction we want. And actually, I'm going to show you 2 ways to do this, okay? So that's our target reaction. What reaction is this? We're given a heat for combustion of methanol. And then this is the amount of heat that's released when we combust methanol. So we have to use, that's the reaction we're going to start with. What reaction is that? It says it's a combustion reaction. So what are our products? What are our products? What are our reactants? What's the reaction associated with this heat?
Carbon, half oxygen, 2 hydrogen.
Carbon and half an oxygen to what?
2 hydrogen.
No, we're not forming methanol. We're combusting it. So what does that mean? We need the reaction that goes with this one. What reaction is that? It's a combustion reaction involving methanol. How do I write that out? Well, I know it involves methanol, so I'm just going to write that down. So there's my methanol.
And then you add O2.
That's right, I'm adding oxygen. When I combust something, it means I'm rapidly reacting it with oxygen. That's what combustion means. So I'm burning methanol. So I need me some oxygen. So I've got my methanol, I've got my oxygen. So that's a liquid, that's a gas. And what are my products going to be? Basically, when I burn anything. So I've got a hydrocarbon there, and I'm burning it with oxygen. What are my products going to be? Pretty much always the same thing.
The methanol.
So if I burn methanol with oxygen, my product's going to be methanol?
Methanol gas.
No, I'm burning it. I'm combining it with oxygen. I'm not changing the state of it. I'm literally burning it. And when I burn something, what products do I get?
Would it be CH3 plus water?
CH3? No. No, basically when I burn anything, what do I get? Anything with carbon and hydrogen in it. Yeah, ignore the oxygen for right now.
CO2.
Yeah,
Carbon
I get
dioxide.
CO2, gas. And what's my other product?
Water?
Water, exactly. That's what you usually get when you burn something that has carbon and hydrogen in it, and oxygen for that matter. You get CO2 and you get water if you get complete combustion. Now we need to balance it, right? Because we need a balanced equation. So I got one carbon on the left, I got one carbon on the right. I have 4 hydrogens on the left, but I only have 2 on the right. So what am I going to do there?
Two hydrogen in front of the product. The 2 in front of water.
Yes, 2 in front of water. That is correct. And, but our oxygens are not balanced. So in this instance, we can put a half where we want because we are combusting exactly 1 mole of methanol. You see? So basically I can put whatever I want in front of the O2 to balance my oxygens. So how many oxygens do we have as reactants? How many oxygen atoms?
3.
We have 3, right? There's 3 oxygens as reactants. And how many do we have as products?
4.
4. Now, usually we would have to balance this reaction, we would put like we put 3 over 2 here, right? Or 1.5, whatever you want it. And then we'd have 4 on this side and 4 on that side. And then we'd multiply everything by 2 so that everything would balance and we wouldn't have any half numbers. But this is unique in the fact that we have to have 1 mole of methanol and 1 mole of methanol only. And so because of that, we can leave a 3 over 2 there. So what that means is that for every mole of methanol, I need 1.5 moles of oxygen gas to combust it all. That's all that means, okay? But like I said, if we're usually balancing this reaction. We don't want any halves or thirds or fifths or whatever. But when we're dealing with a formation reaction, it always means one, just 1 mole, okay? So we have to make sure that everything else fits with our 1 mole of our reactant. So, so we know from this reaction, our delta H is minus 726.6. Okay, so there's 2 ways to approach this question. We can treat it as a Hess's law question and look for our reactants and our products. And we can also, so basically this is our target reaction. Oh, wait a minute. This is our target reaction. We want to add and subtract all the other reactions until we get that. So let's do it that way first, and I'll show you the second way. And hopefully we get the same answer. So we have reaction A. That's A. That's B. And this one is C. So I am looking for, this is our target. So I want to have carbon. I want 1 mole of carbon as a reactant. Where am I going to find that?
Equation C. Equation A.
Equation A, yeah. So A, and it looks like it gives us the right amount too. So let's put carbon plus O2 gives us CO2. And what's the heat associated with that?
Uh, 393.5.
Minus 393.5. Yeah. So minus 393.5. Now I want 2 moles of hydrogen gas. We're going to get 2 moles of hydrogen gas.
B.
B. Yeah, so we're going to take B, you're going to multiply that by 2. So 2H2 plus O2 gives me 2 waters. And what's the amount of energy associated with that?
We have to multiply by 2 the temperature as well.
Not the temperature, the heat.
Yeah, the heat.
Yes, yes, we do, because we have twice as much product, so there's twice as much heat involved. So that's my delta H this time.
Negative 571.6.
571.6. Okay. I'm going to leave the oxygen till the end because there's oxygen all over the place. So I have my carbon, I've got my hydrogen. So let's do methanol. So I need methanol as a product. So where am I going to find that?
You have to flip C.
Yeah, let's flip C. So that would be CO2 plus 2 waters makes CH3OH methanol plus 3/2 of O2. And so what would be the energy associated with that?
You have to multiply 7 to 6.6 times 1/2.
We didn't change anything, we just flipped it.
Oh, then it would be negative 726.6.
Nope. We flipped it, remember? What do we do when we flip the reaction?
Positive 726.6.
Positive, yes, so it would be positive 726 because we flipped it around, 0.6. All right, now let's see if we can cancel some stuff. All right, so what can we cancel out?
2 H2Os.
Yeah, there's water on both sides, 2 moles of water on both sides. So we'll get rid of those. What else can we get rid of?
Carbon dioxide,
Yep. So how much carbon dioxide do we have on both sides?
1 mole.
1. Yeah, we have 1 in the first one, and we, as a product, we have 1 in the third one as a reactant. So we can get rid of that. What else can we cancel?
O2?
Can we cancel it completely?
No.
No. So what do we do?
We're adding it, so it's going to be 2O2.
So it's going to be 2O2 where?
The reactant.
Yes, so we have 2 moles of oxygen as reactants. And how much do we have as products?
3/3. 2/3. Oh, 3.
3O2, 1.5. So we have 2 moles of oxygen as reactants. We have 1.5 moles of oxygen as
We have
products.
half left.
Yeah, what's our net amount of oxygen and which side is it on?
It's going to be on the left side at half O2.
That's right. Yeah, so we cancel that, and change that to 1/2. So that is our net amount. Now, if it was more on the product side, we'd be left with 1/2 mole of oxygen on the product side, but it was on the reaction side. So let's have a look. Is that the reaction we're looking for? We have 1 mole of carbon and 1/2 mole of oxygen and 2 moles of hydrogen gas give us methanol. And that's the target reaction, right? That's what we're looking for. Cool. So what's the amount of heat associated with that reaction?
Professor, in the first one, why you change it to half O2?
That's the net amount of O2 I have left on the reactant side.
But you said C plus O2, it should be had CO2.
Yeah, I have 1/2 mole of oxygen left over as reactants.
Okay,
So I just put a half in front of one of them.
okay.
Yeah, I mean, you can cancel them both and just leave yourself with 1/2 mole oxygen out there if you want. You can do that too. That's fine. But just let it be known that you make sure that you realize that there's 1/2 mole of oxygen left over. And that is what you want. In the target reaction, there's 1/2 mole of oxygen on the reactant side. So what is my net heat when I add up these 3? What's my delta?
Negative
Oh, go ahead.
0.5.
What is it?
Negative 238.5.
That's right. 0.5. So that is the number. What are my units?
Kilojoule per mole.
Kilojoules. That's right. So minus 238.5 kilojoules per mole. So the question was, calculate the heat of formation for liquid methanol. So that's our reaction. That was our target reaction, and that's the amount of heat. We can even look that up. You can look that up right now if you want it. To say, you know, heat of reaction or heat of formation methanol and see what you get. So that's one way of doing it. There's another way of doing it. You want to see the other way of doing it? Yes, we do.
Yes.
Whoa. Oh, wait a minute. No, that's, oh, never mind. No, that's sorry. That's a different reaction. No, that's the way to do this one. There's a couple of ways for some other reactions, but yeah, this one, that's the only way to do it. Sorry.
Can you just show me the last one when you did CO2 plus H2O?
I'm sorry?
The last one.
The last what?
Plus 2H2. From where you get it?
I don't know what you're asking. Which?
The last line that you wrote. The last line.
The last line that I wrote.
Yeah, from the three equations we calculated already together.
Okay, so what?
How you get CO2 plus 2H2O, then CH3H.
These are the things that didn't cancel out. So what didn't cancel out was 1 mole of carbon, 2 moles of hydrogen gas, and a half a mole of oxygen. Everything else canceled out. Those are the three things that were left over on the reactant side. The only thing left over on the product side was methanol. Yeah, that's how we do these. We basically try and cancel everything out that's on both sides. We basically were adding all the reactions together.
Okay.
So we can take all the reactants from all the reactions and add them together, and all the products from all the reactions and add those together too.
Okay.
Okay. So have a look through, see. Oh, yippee dogs, hooray.
Can we do 4?
We can do 4.
If it is hard.
Yeah, it's just basically the same sort of question. Slightly different. This one we could do 2 different ways. So let's do this one 2 different ways. So what's the very first thing? So we want to calculate the reaction associated with the combustion of methane. So on the bottom there, we sort of start it, sort of giving you what the start of that reaction is. What are my products going to be?
Carbon dioxide plus H2O.
Yep, good old carbon dioxide and H2O. Okay, so is that balanced?
The water is not balanced. The hydrogen.
Yeah, we need to balance the hydrogens. So
Put 2 in front of hydrogen.
put 2 there. And now, what else do I need to do?
Get 2.
Oxygen.
I need 2 oxygens, right? I think that balances everything, right? It's 1 carbon, 4 oxygens, 4 hydrogens. Yeah, we're good to go. So this is the reaction. This is our target reaction. This is what we want to figure out. What's the heat associated with that one? So we've got 3 other reactions up there that we can use. So like I said, there's 2 ways to solve this. The first one It's basically using Hess's law like we have been. So the heat of formation of CH4 is what reaction? We sort of just went through that. What reaction is that?
Combustion.
Nope. We're forming CH4.
Oh, okay. Mhm. Heat
Remember,
form-
there's a very specific reaction that's involved with the heat of formation of something. So what would we be forming CH4 from?
C and H.
Not C and H. C,
H2O?
yes. C and what?
Hydrogen.
Oxygen.
Oxygen. There's no oxygen in CH4.
Hydrogen.
What form of hydrogen?
2H2.
Yes, hydrogen gas. That's the important thing. Because remember, it's the most stable form of all the elements that are in that molecule. So the most stable form of carbon is solid, graphite. And the most stable form of hydrogen at standard temperature and pressure is hydrogen gas. So that's right. And then we also know what heat is involved with that. What about CO2? What reaction is that? So we know it's going to be carbon again. And what else?
Oxygen.
O2.
And what, yeah, O2. And we know what heat that is, that one. And what about water?
H2.
with
Mhm. Plus what?
O.
O2.
Mm-hmm.
It's not balanced.
So how many? So we need
You
just
put a
half.
2 in front of hydrogen.
No, because I have to have exactly 1 mole of water. So I'll put a half mole there. That's how I'm going to do that one. Okay. So I'm going to take these 3 reactions and use those to make this. Okay. So here's my CH4. There is my CO2. There's my water. All right, so I need to make our target reaction. So where's my CH4 at? Where am I going to get that from?
The first one.
From A, right? So CH4 X C and 2H2. And the delta H for that one is minus 74.8. Okay, so I got my CH4. So products, where am I going to get? I need CO2 as a product.
The second one, B.
You have to flip.
Yeah, I need to flip it. That's right. I need to flip it. So that's going to be C plus O2 makes CO2. That gives me, so what's going to be the delta H for that one?
Positive 393.5.
Oh, duh. I screwed this up. That makes CH4. Idiot. Makes CO2. Makes water. Idiot. So this first one has to be flipped. So that one's positive. Yeah, I screwed that one up. Sorry about that. But the second one is the right way. So that's negative. So that's negative 393. Sorry, I've confused myself here. 0.5. So now we need water as a product. So where are we going to get that one?
Reaction C.
Reaction C. And what else do we have to do to it? That we need 2 moles of water, so that's not going to give us enough water.
You have to times it by 2.
Yeah, multiply the whole thing by 2. So 2 moles of hydrogen plus now a whole mole of oxygen makes 2 moles of water. And what's our heat associated with that?
It's you have to times the whole thing by 2. Is that right?
Mm-hmm. Oh. Oh man, making me do my own math. You people are the worst. Come on. How much heat is that?
Professor, I have a question. How
Yep.
come you left out the
It's
O2?
negative 5.
Oh, because I'll get to that at the end, because there's O2 all over the place. There's O2 in the second reaction and in the third, so I figured I would wait till the end and see what I have to
when
do.
we do the equation on the test, should we leave that out as and then
Well, you
towards
don't
the
leave
end
it out. I mean,
as
you
well?
have to take it into consideration. But I would leave
But
it.
towards the end.
Yeah, leave it till the end. The same way that when we're balancing combustion reactions, we leave that O2 to the very end. We balance the carbon first and the hydrogen second, and then we screw around with the O2 when we have to. It's the same sort of thing here. So how much heat for the formation of 2 moles of water?
Negative 142.9.
Huh?
Multiply 2.
Oh, I'm sorry.
571.6 negative.
Negative, yes. Okay, now let's see if we have to do anything with the water. So what can we cancel? What do we have in common on both sides that we could cancel?
The 2 hydrogen.
Yeah, we got 2 moles of hydrogen as product here and as reactant here, so we can get rid of that. What else?
Oh, you have the O2. Oh wait, no, sorry. That's it.
Nope, there's something else we need to cancel.
The carbons.
The carbons, yes, I have a mole of solid carbon here and I have a mole of solid carbon there. So I want to eliminate them. So now when we add everything together, I have 1 mole of methane. I have 1 plus 2 moles of oxygen. And on the product side, I have 1 mole of CO2 and I have 2 moles of water. And that's our target. That's what we're looking for. So basically, I can just add these together. So when I do that, what do I get? Yeah, a lot of quiet. The math isn't that hard, people. Just need to add those three numbers.
Negative 890.3.
Yes, minus 890.3. So that's one way of doing it. There's also another way of doing it. Since we have standard enthalpies of formation of everything we need, we can take a shortcut and do it another way. So anyone remember how we do that? How do we do that when we have, so here's our reaction. So CH4 plus O2 gives us CO2 plus 2H2O. What's the other way we can calculate this reaction. Do you remember there's a method? If we have the heat, if we have the energy of formation of all our reactants and all of our products, what can we do?
Divide.
We can do what? We can divide? We actually don't divide. We sum. What do we sum?
We sum the change of the heat between CO2 and H2O.
And what do we, that's right. So we basically, we take the heat of formation of all the products and we sum them together, right? You remember this, we sort of sum heat formation products and we subtract from that the sum of the heat of formation of the reactants. Does this look familiar to anybody?
Okay.
We just did it last night. And the way to remember this is that when we form products, we're bonding together the products, right? We're forming products. So for all the products, we're forming all those bonds that make products. So that is going to be, that's what the reaction is. So we add those together. When it comes to the reactants, we're doing the opposite of forming them. We're actually taking them apart. And so we subtract those because we're busting them up. We're not forming them. We're doing anti-forming. So we're taking them apart. So we subtract those. So we take all the products and we subtract all the reactants. So let's just do that. See if we get the same answer. So so we want the heat of formation of CO2 plus heat of formation H2O minus the heat of formation of CH4 minus the heat of formation of oxygen. To see how that works, so here's our two products over here, and then negative sign. These are our two reactants. What else do I need to do? I've deliberately made a mistake. What's my mistake?
You put negative. Oh.
Nope, they should be negative.
Oh.
But there's a mistake there.
Water.
What mistake did I make with the water?
Here's 2.
There you go. Yeah, there's 2. I made 2 moles of water, so that's twice as much. Remember, whatever you do to the reaction, you have to do it to the heat. So in this reaction, there's 2 moles of water being formed. That means I got to take into account the 2 moles of heat that go along with it. So yeah, so I need to multiply that by 2. Excellent. Now I just add them together. This part's going to be pretty straightforward. So what's my heat of formation of CO2? It's right on the page.
393.5.
Nope.
We changed the sign, right?
No, we don't change the sign. That is the heat of formation of CO2. I don't change the sign.
So negative 393.5.
Yep, negative 393.5. What about water? So it's going to be plus 2 times something. That's my water.
285.5.
Nope.
You have to times that by 2.
Negative 285.8. Always remember the signs are really, really important here. So we need to get that right. So minus, what's my heat of formation of CH4?
Negative 74.8.
Yep, negative 74.8. And then minus, what's the heat of formation of oxygen?
We don't know.
You should. It's the most stable form of that element at room temperature. What's the heat of formation of it?
-8.9 to 0.3.
Nope. That's the combustion for methane.
Oh, for oxygen.
Mm-hmm. Heat of formation of oxygen, molecular oxygen. Remember, what was the heat of formation for all the most stable forms of atoms at room temperature? They were all the same. So O2,
0.
0. Yeah, O2 is the same as H2, it's the same as F2, which is the same as Cl2, which is the same as carbon, which is the same as sulfur 8. They're all the most stable forms of those elements at room temperature. So that is 0. So we don't even need to consider that.
Professor, I have a question. When
Yes.
we add this, the delta HF, do we need to change the sign? I noticed like you put it all the same, like we did not change any,
No, you don't change the sign.
but because now I have like something as reactant, something on the product.
You subtract, you just take into consideration the heat of formations. Just remember that there's going to be a plus sign in front of all of the products. So don't change the sign.
Okay.
And then subtract whatever's in the reactants. Don't change the sign. So just sum everything that is products without changing anything. And then add up all the reactants together and then subtract that much. But don't change any signs. You'll run into trouble if you just remember to add one and subtract the other. Don't. That's why instead of changing the sign, I just put a negative, subtract it here and then a negative inside. That way I don't forget that what I'm doing. If I change the sign, then I might go, okay, then I subtract and I change the sign, and then you don't want to do that. So don't make it harder than. I can't remember anything, so I need to not leave little traps for myself. So now we just add everything together. So what are we going to get when we add everything together?
You're going to get the same thing on
Hope
top.
so. You get minus 890.3.
Yes.
Yeah, you do. So you get the same thing, because basically we're doing the same thing when we're doing a Hess's law. All we're doing is we're breaking apart molecules and forming other molecules. So we're counting all the bonds that are being broken and all the bonds that are being formed. And that's exactly what we're doing here. We're taking into account all the bonds that are broken and all the bonds that are formed. But instead of using other molecules, we're just going right to the source and using strictly the atoms they came from. But we're doing the same thing, because at the end of the day, net, it's exactly the same number and type of bonds being formed and broken. So we should get exactly the same answer. And we did. So yay for us. Okay, do you see how that works, or why that works? Basically, you're breaking and forming exactly the same bonds. You may be doing them with different molecules, but when you sum them all together, you're breaking and forming exactly the same number and type of bonds with either method. But sometimes we can't use this method because we don't know what the standard enthalpy of formation is. And so if we don't know that, then we have to go with whatever the reactions were given. But so this is a hint to you. If you see delta HF, you can probably just do this. But it's really important that you remember the standard enthalpy, because I'm not going to remind you, the standard enthalpy of the most stable form of atoms is 0. And that means O2, but it also means just carbon by itself. All right? Okay. Right, do a couple more, call it a day. Go have a nap. Which ones look juicy?
Can we do number 6?
I don't know. Can we? Let's see.
Or number 5.
Or number 5? It's okay. Number 5, I think number 5, because there is percent. So
Yeah, five has got some,
Yeah.
got a little twist to it. Yeah, 6 is pretty straightforward. Yeah, let's do 5 because it's got a couple things going on. So here's our combustion of methane. So I guess we're supposed to. We have to go back to what our answer was in 4. You need to figure out, but I think we just did that, right? Well, yeah, we just did this one. So what was our answer? It was -8 something. So we need to use that answer to answer 5.
-8 and 0.3.
So delta reaction is what? -8.
90.3.
Okay, kilojoules. Okay, excellent. So we want to raise the temperature of 250 grams of water from 20 to 100. So what do we need to calculate for that? We need to raise the temperature of something. What does that mean? What does it take to do that?
The boiling point.
Well, we don't need the boiling, but it gives us the 2 temperatures. But what are we actually calculating?
Change in heat.
Change in heat, exactly. We're talking about Q. So we need to calculate Q. So we're raising water. So what 3 pieces of information do we need to calculate Q?
Specific heat of
Yeah,
water.
we do. And we know that's 4.184 joules per gram per degree C. What else do we need?
Times mass.
So what do we have? What's mass for this one?
250 grams.
250. Mm-hmm.
Time.
And what's the third thing we need?
Change in temperature. Delta T.
Mm-hmm. Yep.
80.
80. So how many joules is that?
Eight 3680.
83680 joules. Okay. How many kilojoules is that?
83.68
Yeah.
kilojoule.
Yep. So we need 83.68 kilojoules of heat from a reaction. So what does this tell us? What does this actually mean? How much methane is involved with that? It says when we burn methane, we get 890.3 kilojoules. How much methane? Is it a gram? Is it like 50 grams? I have no idea how much. When you see delta H, what does that mean?
Change.
The delta means change. What does the capital H mean?
Heat.
Yes, but if for a specific amount of something. Q also means heat. H means something special. It's so special.
Formation?
Nope.
Oh.
Q is heat. H is also heat. But there's more information associated with delta H than Q. What does delta H actually mean?
Enthalpy.
That's right. It is enthalpy. Enthalpy of what?
Of the reaction.
Enthalpy of the reaction. How much reaction?
1 mole.
1 mole. That's the key. That's the key to the whole thing. You have to remember that delta H reaction or delta H formation or delta H anything means per mole. That's the whole point of giving it the big capital H, because it tells us there's something very important. Or else we just use Q. Q means heat. Yeah, you know, that's all. Q is just heat. But Q is the heat for any reaction, of any amount. You know, if I take, you know, five grams of octane and burn it, I get heat from it. But I don't get delta H until I've made the conversion for per mole. That's the key, because then I can compare my heat to somebody else's, to like people around the world, and we should all get the same number. So that means minus 890.3 kilojoules per mole of CH4. That's what that means. So our question is, what mass of methane will give us this much? And the other thing we have to consider is that only 58% of that will make it to the water. So does that mean, are we going to need more than this or less than this? Are we going to need more than our 83 kilojoules, or are we going to need less than 83 kilojoules? So if the heat we're going to get from the methane, only 58% of it is going to be transferred to the water and heated up. So we figured out that we would need like 84 kilojoules. Are we going to need more than that now, or are we going to need less than that?
Do you mean the balance?
The balance. No, I just mean if little more than half of that heat is actually going to be heating the water and the rest is going to be lost, do we need to burn more methane or less?
Less.
Now remember, would it be easier if it was like half? If only half of the heat was used, would we need twice as much heat to get what we want, or would we only need half as much?
Seems like twice.
Yeah, it does, right? Yeah, we're going to need more, because we're not getting all. It's not 100% efficient. It's only 58% efficient. So it means that a lot of that heat is going to be lost. We want to end up with 84 kilojoules. We're going to lose whatever amount of methane we figure out gives us 84 kilojoules of heat. We're not going to get all of that. We're going to get less than that, but we desperately need 84 kilojoules. So we're going to need more. than the amount of methane that would give us 84 kilojoules. We're going to need more than that. And how much more are we going to need? How are we going to figure out how much more we actually need? So we
Wouldn't you have to do the Hess?
Nope, don't have to do anything with Hess's law. It's a very easy conversion.
You need to convert the percent to
To gram? To no, to
Yeah, we convert the percent to a fraction, right?
Mhm.
So we're going to multiply by that fraction or divide by that fraction?
multiply.
But if I multiply by 0.58, that's going to give me less heat than I need.
divide.
Yeah, so I need 83.86 kilojoules. And basically, I'm only going to get that much of it. I'm only going to get 58%. So I need to multiply by 1 over whatever amount I'm actually going to get. And that will tell me what I need to get. Okay? So 83.68 divided by 0.58. So I actually need 144.3. So look at it this way. This tells us how much we actually need, because we actually need this much, because what happens is that we're only going to get 58% of that, right? So we multiply how much we actually need by the efficiency that we're going to get it to give us the actual amount that the water is going to receive. You see how that works? So you could have had just like X times 0.58 gives 83.68. That's another way to do it if you want to do that. That gets you the same answer. So basically X amount of kilojoules times 0.58. And then when you do that, what do? You divide each side by 0.58. So now we figured out we actually need 144.3. That's what we actually need to get. So how much methane in moles are we going to need? I need this, and this is the ratio of kilojoules to moles. Tell me how to set up that reaction. So 144.3 kilojoules equals something.
We see now delta H from 20 degree to 100 degree. Do we do something about that one or no?
That's how we figured out Q.
Mhm.
We needed to figure out Q first, because that's when we heat up water, it takes heat, and heat is Q.
Okay.
So I need me 144.3 kilojoules of heat. How many moles of methane do I need to get me there?
Do we do
One.
molar mass, molar mass?
We haven't done that yet.
Mm.
Right now, I'm just asking,
One
how are we
mole.
going to get moles?
Do you have to convert 250 grams into moles of
Why?
CH?
Why? That's water. Why do I need to convert that into moles?
Never mind.
We use grams to figure out Q. Because remember, the specific heat of water is given per gram, not per mole.
Equals negative 890.3.
What do I do with that number?
Disregard.
Man, someone tell me, how am I going to convert kilojoules to moles?
Oh, you would take 1/8. No?
What do I do with it? Take it. What do you mean? Multiply?
No. Oh, yeah, times 1/negative
That's
890.3.
right. That's right. Yeah. So 1 mole CH4 over my, and this is also negative, by the way, because since it's heat leaving the reaction and going into the water, that's heat that's being generated by the reaction. So that's also negative. So yeah, minus 890.3 kilojoules. So how many moles is that?
Zero point 16230.
0.163.
0.16205.
Okay, moles CH4. And then you just convert moles of CH4 to grams of CH4. And by God, I'm not going to do that for you at this point. You should be able to do that. Yeah, so yeah, just cancel kilojoules and you're left with moles. It's always the same trick I've sort of been trying to teach you from the very beginning. What unit do you want? I'm going to put that unit on the top. What unit do I want to cancel? I'm going to put that on the bottom. So in this instance, I want it moles of methane. So that goes on the top. And energy, kilojoules, I want to cancel that. So I put that on the bottom. And that's what this is. That's what we worked out from the last question, is that's how much energy you get from burning 1 mole of methane. That's what delta H means. So there's a lot in this question that you need to remember. You need to remember what delta H means. You need to remember what Q is. Yeah, there's a lot going on. That's why it's a really good question. There's a lot to it, a lot of different parts. So I think we got time to do one more if you want to pick one out. Make it a goodie.
I think we get it.
Can we do
Well,
question?
you get it, Ricky, because you're just a natural genius at these things.
Can we do either 7 or 8?
Let's have a look.
The hardest one. What do you think?
7 or 8. Yeah, they're pretty much the same kind of. They're both like Hess's law questions. No, you just pick one. I don't know.
Let's do 7.
Sure. 7 sound good to everybody?
I don't know. Everyone is silent today.
Yeah, exactly. I think everyone's just burned out. I completely understand it.
No, we are in tension for exam tomorrow. That's why.
Okay, so Hess's law question. We got delta H's. We haven't got heats of formation. So we're going to have to rearrange these particular reactions to get what we want. So We need to look for hydrogen and chlorine as reactants and HCl as a product. So first of all, where are we going to find hydrogen gas as a reactant?
C.
Yeah, I think reaction C is the only place for it, right? Yeah, so reaction C. But we only want half a mole. So what do we have to do to C?
Multiply by 1/2.
Yeah, so that'll be our first one. So 1/2 C is half a mole of dichloromethane plus 1/2 mole of hydrogen plus, well, this is going to be tricky, 3/4 of a mole of oxygen, give us half a mole, Cl2 and water, one mole of water. Okay. And oh yeah, what's our delta H for that one? So what's delta H for that reaction we just wrote down?
Oh, 47.5 kilojoules.
Huh? No. It's the third reaction, not the first one.
Oh, yeah, sorry.
201.25.
Yeah.
Negative 2.
Whoa, negative, yes. So negative 201.3. I'm just going to round. I say never round, but we basically see how everything is just like one digit after the decimal. So I'm just going to leave it like that. And 4 significant digits as well. Okay, so we found our hydrogen. So hydrogen, we're good. So now I need to find chlorine gas. Which reaction has chlorine gas in it?
Reaction to B.
Yeah, B. 2 problems. It's got chlorine as a product and it's got too much. So what are we going to do with that one?
Would you divide?
Yeah, we need to divide it by 2. That's one thing we need to do. So yeah, we need to divide it by 2. So what else do we need to do?
We'd have
Switch to the other side.
flip.
Yeah, we need to flip it. So we need to have 1/2 Cl2 plus 1/2 water makes 1 HCl plus, again, now 1/4 of a mole of oxygen. And what's my delta H for this reaction?
Let's do the math right now.
Yeah, it's good. Let's do that. So we've reversed it and we've divided it by 2. So what's our new delta H for reaction B?
52.5.
Nope. You're close.
Negative 52.5.
There you go. Yeah, because we flipped it. So remember, we need to change the sign. When we turn the reaction over, we need to flip the sign because it goes from being endothermic to exothermic or the other way around. So yeah, very important. We remember to do that. So negative 52.5. Now, if you'll notice, we have our hydrogen on the right side, we have our chlorine on the right side, and we have our HCl on the correct side. We have all this other stuff that we need to cancel. So we need to look for things that we can't cancel. And a couple of them jump out. There's this, and there is this. We need to cancel those out. So how do we do that?
You need reaction A to cancel them out.
The reaction A to the rescue. We certainly do. So what are we going to do? We have half a mole of dimethyl chloride, H2, CH2Cl2 as reactant. I want to get rid of that. And I've got COCl2 as product. I need to get rid of that. So what am I going to do? And I have a half mole of each one.
Times it by point. Wait, no.
You have to multiply reaction A by
Mhm.
1.
By 1/2. Yeah.
Oh, yeah. Right.
Let's see that. Let's see what that would look like. So that gives us 1/2 COCl2 plus half a mole of water. Makes half a mole of CH2Cl2 plus half a mole of oxygen. And what would be the heat associated with that reaction?
.23.
23.8, let's say. So plus or minus?
It's minus.
I heard minus and plus. Which one is it? Did we flip it or did we just divide it by 2?
Positive.
So what's the sign?
Positive.
Positive. It's still positive because we haven't flipped it. So that's still positive. I make sure I put my little positive there so I don't forget. All right. So now it's time to take stock and see what the hell we got here, because it's all kinds of things. Let's look for things. Well, we know we can cancel COCl2 and CH2Cl2 because we just added reaction A, so we could do that. So let's do that with them. So get rid of that, get rid of that. I got my there and there. So now we've got all this waters and everything else. So let's do water next. So how much water do I have in all 3 reactions?
One in the first.
Yeah, I've got half here and half there. And how much product?
You have one.
One in the product too. So I'm echoing. Oh, no, I'm not. Okay, so it gets rid of our water. So what else do we need to deal with?
Look at O2.
Yeah, we got oxygen all over the place. Let's deal with that. So how much oxygens do we have as reactants?
Well, you have 1/2, and then you have 1/4.
As products or reactants?
Oh, reactants. 3. Right. 3/4.
Yeah, 3/4. Yeah, we have 3/4 as reactants, and how much do we have as products?
1/4.
You're missing some.
And also half in the second one.
There
So
you go.
all cross out, you know?
Yeah. So we have 3/4 of a mole as reactants, and we get 3/4 of a mole as products. So we can, yeah, I was getting a little worried there when I saw the 3/4. Like, that's weird. You don't usually see those weird kind of fractions, but it worked out. So what do we have left? Let's change colors and see what we have left here. So we've got half a mole of hydrogen, half a mole of chlorine. And those are the only two reactants left.
Mhm.
And my only product that's left is HCl. So there we go.
Yes.
That's a good one. Man, I have to remember this one. That's a good one, because I know you guys are going to be panicking when you see like 3/4 of a mole. You're going to be tripping and just, freaking out. So yeah, I definitely have to remember this question to torture students with on a test.
Just glad that that's not going to be on the exam.
It might be. I might just change chlorine to bromine and just, say, hey, this looks familiar. All right, so what can we do? So we can add C multiplied by a half, B multiplied by a half and switched, and A multiplied by a half. We add them all together and we get our target reaction. So what is our delta H?
-230 kilojoule.
0.0?
Yeah.
All right, cool. Kilojoules per what?
Mole.
There you go. Because that is what delta H means. That's important to remember, because that came up on one of the questions. So Q just means any amount of reaction. It just means the actual amount of heat that was produced by a reaction. So we can convert Q to delta H by figuring out how many moles were involved in that particular reaction. So Q is just sort of just a general form of heat, from anywhere, of any kind. Delta H is very specific and important to remember what that means, because then we're dealing with specific quantities of reactants and
Professor?
products. Yeah.
I have a question. How you get the final answer 230?
We added together our 3 delta H's.
Okay. Okay. Got you.
Yeah.
0, 1. Okay.
Yeah, it's the whole point is that we can, once we add the reactions, we can also add the heats. That's what Hess's law says we can do.
Okay.
Hess was very wise. Yeah, I like this one. There's lots of weirdness. I like it. Yeah, I'll have to think of something just as evil for the test tomorrow.
How the exam will be tomorrow?
Evil? What do you mean, how will it be?
Like how many questions? How it gonna be?
Just sort of like the first one.
So multiple choice, then
Some multiple choice and some questions. I need to go back and have a look at it, because I finished it a week ago. Now I haven't looked at it since. So I need to go back and make sure it's evil enough.
for recitation, the one we did now, it will be included in the exam for tomorrow.
No, it'll be on the final.
Okay. So
Yeah.
How long will we have to turn it in?
From 10 in the morning till 10 at night. I think that's what no, sorry, that's the lab exam on Monday. This one you have till Saturday morning at 10.
Nice.
Yep.
So the one on Monday, we turn it in 10 p.m.
Yep.
So it opens 10 a.m. Monday and turn it in 10 p.m.
10
Monday.
p.m. Yep. Yeah, that's for the folks who are working on the weekends. And some people work on Mondays, so you can't make everyone happy. So yeah, it's basically moved it to Monday, but you have all day. All right. So I will see you at 4:15. And we're going to continue with molecules and shapes and all that good stuff. Okay?
Sounds good.
I will see you then. All right. Have a good afternoon. I'm going to desperately
Thank
try and take a
you.
nap. All right. We'll see you later. Thank you guys.
All right.
Bye-bye.